Welcome back. Today we're going to be talking about the probability models that we've been looking at a little bit in class. And I'm going to wrap up these last two questions by taking you through exactly what it's going to take to solve them. So in this one, we're rolling 7 dice simultaneously, and we're going to find the probability of these outcomes. Exactly 2 threes. And so when we're doing this probability model, what we want to consider is the fact that we've got these 7, 2, 3, 4, 5, 6, 7. And when we roll these 7 dice, there's really a 1/6 probability of getting those 2 threes. Okay, so we're going to find that favorable outcome. That favorable outcome is 1/6 of getting a 3 and then 1/6 of getting a 3. On the other 5 dice, the favorable outcomes are not threes, right? So there's a 5/6 chance that we're going to get our favorable outcome on these. And so we've got 1/6 squared, because that's the number of dice we want to show a 3. And then we've got 5/6 to the 5th power. Because the other 5 dice we've got a 5/6 chance of getting not what we want. So that's the probability that we're going to get those 2 threes. Except that that's on the first 2 dice. Okay, so if we have all the 7 dice in a row, what if it was the second and third? What if it was the third and fourth, fourth and fifth, first and sixth? And so we have to consider the number of ways there are to arrange these dice, or the number of ways that any 2 dice could show it. And so we really want 2 of the 7 to show 3. So what we're going to do is we are going to combine 7 things 2 at a time into threes, and this is the probability of getting a 3. So there's 7 choose 2, so this is equal to 7c2 times 1/6 squared times 5/6 to the 5th. Because 7c2 is 2 of the dice, only 2. But how many ways are there to combine these dice 2 at a time to get our answer? And so when we calculate that and we put that into our calculator, the probability of that happening is 0.234, so 23.4%. Second one, exactly 3 threes. Well, it's kind of the same sort of idea, except we're not taking 2 at a time, we're taking 3 at a time. And so it's 7c3, 1/6, and that's going to be 3 because we want 3 of them for a favorable outcome of 3. And then 5/6 to the 4th, because 4 of them are not going to show. And then that, when we put that into our calculator and calculate it, we're going to get 0.078 or 7.8% probability that happens. Okay, so the trick is taking that 7c2 or that 7c3. How many ways could we combine the dice 3 at a time where the 3 of them have the favorable outcome that we want? On this last one, at least 3 threes. Well, this means at least 3. It could be 3 or 4 or 5 or 6 or 7. And so there's actually 2 ways to do this. To combine these probabilities is to say it could be 2, or sorry, it could be 3, it could be 4, 5, 6, or 7. And so because this is a combination is not the right word, it's a sum of all of these probabilities. So we have to add the probability of 3 plus the probability of 4 plus the probability of 5 plus the probability of 6 plus the probability of 7. And when we do that, we get 7, 3, 1/6 to the 3rd, 5/6 to the 4th, plus 7 combined 4 at a time, 1/6 to the 4th, and 5/6 to the 3rd. And this should look familiar. This is that binomial probability model that we were talking about, and you're going to see that it looks extremely binomial here. 1/6 to the 5th, 5/6 to the 2nd, plus 7 to 6, 1/6 to the 6th, times 5/6 to the 1st, plus 7, all 7 of them, and this would be 1/6 to the 0, and then, no, 1/6 to the 7th, and then 5/6 to the 0 power. Okay? All of those. And so sometimes in probability, you get these really long problems where we're saying it's this, or this, or this, or this, or this, or this, or this. And we know that the sum of all those probabilities, sum of all possible probabilities, is 1. So these aren't all the possibilities, so it's less than 1. Another way to consider it would be to say 1, or all the possibilities, minus what doesn't satisfy. So that would be the probability of 0. So it's 1 minus probability of 0, plus the probability of 1, plus the probability of 2. So it's 100% chance to get what we want, minus getting 0, 1, or 2, because those don't satisfy. So what's left is everything that would satisfy. So you could do it like this: 1 minus, and then you have the probability of 0, which would be 7, 0, times 1/6, and none of them are showing, so this is to the 0 power. And then this would be 5/6 to the 7th. And so the key is to get all these in parentheses because it's all of these probabilities. So 1 minus all of these probabilities. And this would be 7, choose 1, 1/6 to the 1st, 5/6 to the 6th, plus 7, 2, 1/6 to the 2, 5/6 to the 5th. Either way, you get the same answer. Whether you add up all the probabilities of what does satisfy, or you do 1 minus what doesn't satisfy, you still get the probability of 0.096. Okay, so there's a 9.6% chance that it happens. Okay, let's look at one more example. Again, playing on this idea that we've got certain things that happen on certain days, or dice, or whatever it is. It's probabilities of an event that has multiple things going on. Suppose the traffic light at the driveway leading into a school is red for 55% of its green, yellow, red cycle. During a 12-day period, find the probability that a school bus has to stop there on the following number of days. Okay, so let's think about this for a second. Up here, when we did dice, it was 1/6 probability that it is happening, 5/6 probability that it's not happening. In this one, we're looking at exactly 4 days out of a 12-day period. So any 4 of them. So 12 things, I'm taking them 4 at a time. So I need 4 of those 12 days. And the probability that it's that it's red is 0.55, and that's for 4 of the days. So 4 times. So these 4 days, it's 0.55. But the other part is 0.45, because that's the part that it's not red, not satisfying what I want. But on those, because it's exactly 4 days, on those days, the favorable event is that it's not red. Does that make sense? So 0.55 is the probability that it is favorable on that day, that it's favorable that it is red. And then the other 8 days is that it's not red, because we need just exactly 4 days. And so when I end up doing this little bit of math here, I get, let me look through my notes here, 0.076. Okay, so that's exactly what happens there. All right, so what about this at least 9 days? So at least 9 days is going to be 9, 10, 11, or 12. Well, what's the probability of 9, 10, 11, or 12? It's the probability of 9 plus the probability of 10 plus the probability of 11 plus the probability of 12. Okay, so it's at least 9. So it's 12, 9. And my favorable event is 0.55 to the 9th, 0.45 to the 3rd. Once again, I'm dealing with 12 days, so if exactly 9 days, 0.55 is my favorable event. So my other 3 days have to be that 0.45 where my favorable event is not. So I'm going to add to that 12, 10. 0.55, and notice up here I did 1/6. Down here I can use this 0.55 because probability can be expressed as a percent or as a decimal. And this would be 10, and this would be 0.45 to the 2nd power plus 12, 11 times 0.55 to the 11th, 0.45 in parentheses to the 1st, plus 12, 12. That's all 12 days, 0.55 to the 12th power there. Okay, so that's exactly what I want. And when I add up all these, it is 0.134, which is equal to 13.4% chance that that happens. Okay, so that's how these work. Just making sure you're breaking down events and seeing, calculate the probability of that event, and then figure out the number of ways that there are to have that event happen, and multiply those, and you've got your probability there. All right, guys, thanks for watching, and we'll see you next time.